Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden magic that makes our entire digital world possible: data compression.
I mean, seriously, think about it. It just doesn't seem possible, right? But it's not magic. The answer is hiding in plain sight. And it's all about a brilliant set of ideas around information, surprise, and the art of making some really smart sacrifices.
Look, we are generating an absolutely insane amount of data every single day. We're practically swimming in it. And the only way we manage it all is through one core principle: compression. At its heart, compression is just about one thing: finding and getting rid of repetition, or what information theorists like to call redundancy.
To really get this, we have to talk about a concept called entropy. And honestly, the best way to think about it is as a measure of surprise. So imagine a string of 1,000-letter A's. There's zero surprise there, right? That's super low entropy, and it's incredibly easy to compress. You just say 1,000 A's. But a totally random string of letters and numbers? That's high entropy. It's full of surprises, and it's way, way harder to shrink down. Now, this isn't just some abstract idea. There's a fundamental rule called the source coding theorem, and it proves that entropy sets the absolute hard limit for how much you can compress something without losing a single bit of information.
So, when we decide to compress a file, we immediately hit a fork in the road, and this one choice is critical. It determines our entire approach and leads down two very, very different philosophical paths.
And this is the core trade-off. On one side, you've got lossless compression. Its entire goal is perfect, bit-for-bit reconstruction of the original. This is non-negotiable for things like a text document or computer code, where changing even one character could be a total disaster. Then on the other side, you have lossy compression. Here, we're willing to strategically throw away some data to get much, much smaller file sizes. This is the secret sauce behind all your streaming videos in your music library.
All right, so let's go down that first path: the quest for perfection. This is the meticulous craft of shrinking data while making absolutely certain that every single bit can be restored perfectly.
A really classic, beautiful example of this is something called Huffman coding. It is so clever. It works by looking at your data and figuring out how often each letter or symbol appears, exploiting that low entropy, that predictability. Then it does something brilliant. It gives the most common symbols, like the letter E in English, a super short code, and the really rare ones like Q or Z get a much longer code. When you add it all up, the total message gets way shorter.
Now, that same idea of finding patterns gets even more powerful with methods like lempel-ziv or LZ77. This is the engine that runs the zip files you use all the time. Instead of just looking at single letters, it's smart enough to spot whole repeating phrases or chunks of data. It then replaces that chunk with a tiny little pointer that basically says, hey, just copy the sequence you already saw a few hundred bytes ago.
So this begs the question: what's the absolute theoretical limit? How small can you possibly go? Well, that leads us to this kind of mind-bending concept called Kolmogorov complexity. It defines the true compressibility of something as the length of the shortest possible computer program that can produce it. Think about it. A simple repeating pattern has a tiny program, but pure total randomness, there's no program shorter than just writing out the data itself.
But, and this is a huge but, here's the incredible twist. While Kolmogorov complexity is the perfect ultimate yardstick for compressibility, there's a catch. It's uncomputable. There is no magic algorithm that can just look at any old piece of data and tell you for sure what its shortest possible description is. It's like this theoretical North Star we can aim for, but we can never actually calculate it.
Okay, let's back up to that fork in the road and now explore the other path, what I like to call the art of the compromise. This is where we willingly accept small, often completely unnoticeable losses in quality in exchange for massive, absolutely game-changing savings in file size.
This entire world is governed by something called rate distortion theory. It doesn't just ask, how small can we make this? It asks a much smarter question: okay, for a certain amount of quality loss that we're okay with, what is the absolute minimum number of bits we need to represent this? It's a whole mathematical framework for managing that delicate balancing act. Just picture it like a slider. You can crank it all the way to one end for maximum fidelity, a perfect copy, but a giant file. Or you can slide it all the way to the other end for maximum compression, a teeny tiny file, but you're going to see some obvious quality loss. Lossy compression is all about finding that perfect sweet spot on the slider for whatever you're trying to do.
So, how do they actually pull this off? Well, one of the key tools in the toolbox is something called a wavelet transform, which you'll find in formats like JPEG 2000. It breaks an image down into different layers of detail, kind of like separating out the broad shapes and colors from the superfine textures. This lets us just throw away the finest, almost invisible layers of detail that our eyes probably wouldn't have noticed anyway, while keeping all the crucial stuff that actually makes up the image.
But what if we could be even smarter? I mean, what if instead of grabbing a ton of data and then working hard to throw most of it away, we could just capture only the important bits right from the start? Well, a newer technique called compressed sensing is completely changing the game.
This is where it gets really, really clever. It turns out that for a lot of real-world signals, think medical scans or radar, you don't actually need to capture all the data in the first place. Compressed sensing lets you take far, far fewer, smarter measurements, and then use some powerful algorithms to rebuild the full, high-resolution signal from that incomplete information.
And this is a true paradigm shift. The old-school methods worked on a brute force principle. You have to sample a signal at a really high rate to get it right. But compressed sensing says, hey, if you know that this signal has some kind of simple structure under the hood, if it's what they call sparse, you can get away with way fewer samples. It's a move from brute force capture to intelligent acquisition. So let's bring it all home. How do these two paths, this quest for perfection and this art of the compromise, actually come together and shape the digital world you live in every single day? Well, you see it literally everywhere. That lossless compression is humming away inside the zip files you email and every text document you write. That lossy compression is what makes it possible to stream a movie tonight or listen to a podcast. And that incredible compressed sensing technology, it's powering faster, higher resolution MRI scans that are literally saving lives. These ideas are constantly at work, quietly making the impossible possible.
And that really brings us to the final thought here. The story of compression is really the story of our ability to find patterns and decide what's truly important. As our data creation explodes, this journey is nowhere near finished. The next breakthrough that will completely redefine our digital world is out there, just waiting to be discovered. Thanks for joining us.